But did you see in our group chat?
All right, everyone.
Like grayed out.
Thank you for coming to our third lecture. Hopefully this one will be a little bit shorter than the last one. And we're going to be talking about motors and how we're actually going to get the car to move. And we're in for a really good time. So get excited. Before we get started, there's a few announcements regarding IEEE stuff in general. First of all, there's IEEE General Board is now out. So if you want to sign up for General Board, you're just basically going to be grouped up with a few upperclassmen slash IEEE officers, and you're going to form like a little community. You'll get like academic help, some mentorship. You can ask about classes and also just make some friends in IEEE. So we definitely recommend signing up for that. Anyway, and this is the application, so if you want to try and sign up for that, please do so there. Yeah, so you can join a GB with me, or one with Prem, or one with any of your other favorite officers, or other random people that are part of IEEE. All right.
Next up is Idea Hacks, which is basically the largest hardware hackathon in the West Coast, for those of you who haven't heard of it. It's going to happen in early January, so like week 2-ish. The exact dates are here, January 20th to 22nd. It's a 36-hour hackathon that will go throughout Saturday and Saturday night into Sunday morning. Basically, what you'll do is you'll come over there, no experience required. It's basically a sort of competition where you make something using parts that we give you for free, and then you'll get free food for the duration of the hackathon. There'll be workshops teaching you guys how to do things. We'll also have some light gaming and yoga sessions apparently, so it's kind of cool. It's going to be in the Ackerman Grand Ballroom, and as I said earlier, anyone can show up, no experience required. So we encourage you all to sign up. It's a very fun experience. It's in teams. You can make your own teams and whatnot. You should sign up by the priority deadline, which is sometime next week or the week after. You can find all the exact details on that link, ideahacks.la.
I guess, yeah. So I was just saying, are there any questions about GB or Idea Hacks? Yeah.
For Idea Hacks, you say there's no experience required, but like, what would you do if you don't know?
You show up to the workshops where we teach you stuff,
okay.
and then you do stuff.
You're also part of a team. So
Yeah.
if you're with a team, you can like, I don't know, if you know how to do like breadboarding and circuit stuff, you can pair up with someone who's really good at, I don't know, coding and WebDev or something.
This is true. I was in a team full of electrical and computer engineers, so I had no idea what was going on that side, but I did the more software-y stuff and it worked out. Yeah.
Okay.
Alright, and also, so quick note on assignment 1 and 2. The due date has been officially extended to next Monday because all 12 teams asked for an extension. It's highly recommended that you don't push the deadline further than that because we want you to have time to actually finish the capstone as well. And however, if you do need more time, of course, we'll still accommodate you. And also, if you haven't submitted the assignment yet because you're trying to like make it super duper perfect or something, feel free to just get checked off first and then play around with it later because we're pretty lenient. We just need it to be like somewhat perfect, but with respect to the like counting the dots, it doesn't need to be perfect. We'll take it if it's like good enough. So yeah, that's pretty much it. And now we'll start talking about actual content.
All right. So first, we're quickly just talk about the basic physics of the motor. Maybe you guys remember this from physics, maybe you don't, but we're going to go over it now. So a DC motor is converting electrical energy into mechanical energy, and it does this by generating a flow of electrons in a magnetic field. So if you guys remember what the Lorentz force is, this is basically a force that is applied to charges moving through a magnetic field. And it is a cross product, so it happens with the right-hand rule. So if we look at this here slide, we got the equation for the Lorentz force. As you can see, it's the velocity of the charge crossed with the direction of the magnetic field. So if you look at this diagram, we have this this coil that is inside the magnetic field. And as the charge is going up the screen, you can see with the right-hand rule, it's going to be the velocity is going up, and then you're going to cross that with the magnetic field, and then so you'll see the forces pushing into the screen, which is what that little cross means. And then on the way back, the force is being applied in the opposite direction, which creates a torque. And then if we look again at this GIF, all right, it's not going back. Can you bring it back? Okay. All right.
I'll just
Anyway, once it reaches 180 degrees and it's perpendicular, you can see that the flow of charge actually switches directions, and then the forces switch back, and the motor continues to spin. So that is the basic mechanism. All right, now this is just. All right. Do you want to unplug one of these? Anyway, and so that is the basic mechanism with which we're converting electrical energy into mechanical energy.
I love technology.
Yeah. Okay. So now one issue with this is that we can convert electrical energy into mechanical energy, but we also have to vary how much the electrical energy is, the voltage, and that will control how quickly the motor spins. So here we're going to talk about, or Kramer's just going to talk about how we're going to do that using a Raspberry Pi.
Yep. So before we get started on that, does anyone have any questions on how motors work? It's not really relevant to the assignment, it's just something we wanted you guys to know. Alright, that. Alright, so as Cameron was saying, the problem with battery power and Raspberry Pi powering for the motor is basically, we can power our motor through the batteries, or we can connect it to a pin on the Pi. And that means basically we can turn the motors on or we can turn them off. We can either connect them to the battery or we can have them disconnected. However, as you might recall, motor speed is determined by the amount of voltage supplied, not just whether it's on or off. So you can probably see where I'm going with this. If you have the batteries connected, or the digital pin on the Pi is turned on, you have the maximum possible speed that the motor can go. If you have the batteries disconnected or the digital pin turned off, the motor just doesn't move. And obviously that is not good, because there will be cases where we want to have, the motor moving at half speed or quarter speed or something like that. So as I'm saying, what about all of this region? How do we make the motors go slower? For example, at 50% speed. So the solution to this is in Newton's first law, which basically says that any object at rest or in uniform motion stays at rest or in uniform motion unless acted upon by an outside force, which basically is referring to the idea that this motor is not going to go from 0 immediately to 100. It's going to transition through everything. The outside force that acts on it will pull the 100% speed down to 0 by way of actually transitioning through the other speeds. It's not going to just go from one to the other. So to go at 50% speed, you'll pass through it when you go between 0 and 100. Therefore, the challenge isn't to reach 50% speed, it's to keep it there. And the solution to this is simple. When the motor is going faster than 50% speed, we turn it off. And when the motor is going slower, we turn it back on. So as you can see here, it would look something like this. You have the red line, or I guess it's more pinkish on the screen, but basically the red line represents the speed of the motor, the blue is the voltage we're supplying. As you can see, when the motor is below 50% speed, we supply 100% power, raise it up. Then when the motor goes high enough, we supply 0% power, move it back down. And if you do this at higher frequencies, it gets closer and closer to the line. And at really high frequencies, it just basically hovers constantly at 50% speed, which is what we want. And this is a technique known as pulse width modulation, or PWM. Basically, the idea is by having the pulse high for 50% of the time, we will keep this motor at 50% speed constantly. And that will allow us to have a motor that's not running at full speed or 0, that's somewhere in between. This works for other speeds too, like if you have a 75% high, 75% of the time the motor is high voltage, then you go at 75% speed. At 25%, you go at 25% speed. This is known as a duty cycle. It's the percentage of time for which the pulse is high, as opposed to being low.
Alright, so we run into a little bit of an issue here where the Raspberry Pi can generate only about 5 volts and very limited current. So we're going to have to implement something else called an electronic speed controller, or an ESC. This is a sort of model of what its inputs and outputs. It has a power switch that you can use to turn on and off. It has a controller which provides it with a PWM signal, which it then uses to control the motor, and then it has an external power source that has higher voltage and can also supply higher current than the rest, or than the controller can by itself. So the controller is going to be for us either a remote control, like the receiver for transmitter-receiver pair, or a computer like a Raspberry Pi, and it's going to send a PWM signal to the ESC, which will control how fast it goes.
This works now, so.
Yeah, I unplugged it back in. Anyway, and the external power source allows the motor to run on with the same amount of power that can be generated by the batteries. So it can run on at about 8 volts and with much higher current. Now also, one thing to note, for us, the input PWM signal for the ESC doesn't actually range from 0% to 100% duty cycle. It only has a very small range from about 5% to 12%, and it then uses this and it like maps this to the full voltage scale of the batteries. Now, when we want to do this with a Raspberry Pi, and we're going to use the Raspberry Pi as the controller, and we're going to hook up one of its GPIO pins to the input of the ESC. And I just wanted to take a second to talk about doing this in code. So one of the things you're going to have to do is you're going to have to identify the pins. If any of you guys have worked with Arduino, it's pretty similar to this. You use the GPIO library, and you're going to need to identify the pins. But there's 2 different naming schemes: the board scheme and the BCM scheme. So in the board scheme, you're going to use this line of code to set your code into the board scheme. You're going to be naming your pins based on their number. And you can find this schematic at pinout.xyz, or just look up a Raspberry Pi pin map. Anyway, so this is what you're going to be using if you want to name them by their number like this. But you can also go by name. And if you use set mode GPIO.bcm, you're going to instead refer to them by their name, GPIO 14 or GPIO 15. So if you wanted to refer to pin 8 with board, that would be pin 14 with BCM. And then once you know how you're naming things, you're going to then set it as either an input or an output using something like this, GPIO.setup. And then after that, there's a whole bunch of functions that you can use to control.
Are there any questions so far?
Okay, great. So now for steering, you might think that using a DC motor for steering would work, but it does not, as can be attested by this poor soul. And the problem is that a motor is just basically can go forwards and backwards and has very little real control. And if we wanted to steer with it, we pretty much have to constantly be switching directions based on which way we think we were going, and it would be very difficult to drive in a straight line. Fortunately, we have a solution.
The solution is something called a servo mechanism, which is a fancy, scary name. You'll just hear it referred to as a servo. Basically what it is, it's a motor like the DC motor, except instead of taking in a voltage and outputting a velocity that the motor spins, it encodes that voltage into a mechanical, a certain position. And then it'll just hold that position and resist any sort of movement. So if you try to manually twist it, then it'll just correct itself back to the position that you wanted it to be in, which is what we want in a steering system. We want it to be stable, and servos are very stable. They're also very hard to twist, and we do not recommend you actually twist them when they're being run. That can damage the servo. So like DC motors, servos are controlled by PWM signals. However, instead of the PWM signal controlling its speed, it controls the position. So as you can see here, every servo has a certain range. If you supply a 50% PWM signal, that corresponds to the middle of the range of the servo. 25% would be 1/4 of the way, and 75% would be 3/4 of the way, and so on and so forth. Keep in mind that we're just using 50, 25, 75 as examples, but you guys can use any percentage that you might want for the duty cycle, and the servo will match that. Same with the DC motors. Our PWM signals for servos don't necessarily range from 0 to 100. Our servos range is roughly 6 to 10%, calculated through experimentation. It might differ based on the individual servo, but we just want you to keep that in mind. And to summarize, these are the 3 things we talked about today. We talked about DC motors, which convert an electrical signal into a continuous spinning motion at a controllable velocity. We use them for the wheels of our cars. These are servos. They convert an electrical signal into a specific constant position, and they resist deviations. We use them to steer the cars. And lastly, PWM, which is the actual method of controlling each of these motors. This basically works by taking a digital signal and fluctuating it back and forth, modulating it, as they say, and converting it into an analog signal with a lower average pulse. Any questions before we talk about the capstone? Cool. This lecture was pretty short. But anyway, so now about the capstone. That's not going to be released tonight, it's going to be released later this week to give you guys more time to focus on assignment 1 and 2 and whatnot. But basically what you'll be doing is you will be, I'll turn off the projector. Right. So basically what you're going to be doing is you're going to be taking the camera, you're going to use it to, you're going to use it to detect either a stop sign or an arrow, much like an actual car in the real world might look at road signs. And based on whether it's a stop sign or an arrow, you're going to have it move in different directions. So if the car sees it, first of all, you're going to have to do like a new localization task, just like in assignment 2, where basically you have to observe what the actual sign is. You'll be using various image filters for that. This one is slightly more complicated than just seeing dots on a die, because neither of these are particularly circular, so you're going to have to keep that in mind. I'm just giving you guys all this information beforehand so that once you guys finish the assignment, if the capstone isn't released yet, you guys can just start thinking about it and figuring out what you might do. But anyway, you will have basically 4 things you can see, either the stop sign or an arrow that points up, left, or right. The left or right would indicate that you have to steer left or right, and the up would indicate, of course, that you have to keep going forward. And of course, stop means you just stop. So the general idea of the first part, like I said, is you use localization image filtering that we've taught you so far, and sort of try and decide using your code whether the image that the car is seeing is a stop sign, or one of the 3 types of arrows, or nothing at all, in which case it should just keep moving forward. Then, once you do that, you'll have to actually control your DC motors and your servo to match whatever the sign is telling you to do. Any questions on that? Cool.
Great, thank you.
Yeah, that's pretty much it. Short lecture.
Yeah. Guys out of here. All right.
Huh?